No questions about previous lectures means I gotta ask you some of my own questions. But it'll be good. It will prepare you for the future. Carbonyl carbon, 2 carbonyl carbons. What's the product? What does sodium borohydride do? Is it an oxidizing agent? True or false? False! The crowd screams. It is a reducing agent. So, for however nature is, hydride's going to go there and it doesn't go there. So, we're going to still have our ester without the poopah there. So this aldehyde group gets reduced into an alcohol group. Aldehydes turn into like primary alcohol, and this ester group leaves that alone. Any questions about this reagent? What other reducing agents did we study about in the alcohol chapter? Let's go up lithium aluminum hydride. Now this thing's going to send the hydride there. It's going to send the hydride in there. So this is going to take a little undoing. Lithium aluminum hydride reduces aldehydes and ketone. Let me just draw the intermediate. Here's what we kind of saw in the mechanism. So we looked at also the Grignard reagent attacking carbonyl carbon, and when it attacked an ester, I said I didn't like the type of leaving group because a strong leaving group would go away. So anyway, let's not get too carried away. I'm not sure the order of when we want to do this. Here's what I'm going to do. I'm going to figure out that I got 1, 2, 3, 4, a 5 carbon chain. 1, 2, 4, 5 carbon chain. And if I make this number 1, I'm going to have an OH at number 1 carbon. Number 2, I'm going to have a carbon and then an OH. There's that carbon. Down here, carbon number 5, I'm going to have this other OH. I'm going to make this look a little prettier. Now the ring openings are kind of confusing, so I'm going to come up with a real simple ester, aluminum hydride, followed by protonation. There's the alcohol we get. This thing, once everything's protonated, there's probably some of this. Methanol. You can see 1, 2, 3, 4. 1, 2, 3, 4 on that 4th carbon. It used to have carbonyl. There's the OH. This thing left. There it is. Just how this thing left and becomes this. When this part leaves, you're going to get this OH. Any questions on this? Not stand. Oh, hang on. I got too much. I apologize. I got too much stuff going on here. Let me. Don't erase anything yet. Edit all that first part out. Fix my penmanship. Explain why this synthetic route would be unsuccessful. So in the alcohol chapter, we saw we can make alcohols by substitution. Here's an alkyl halide. There's the nucleophile implied substitution reaction. Absolutely. We learned that for SN2, methyl was the most reactive, followed by primary alkyl halide, followed by secondary, and then say tertiary is right. Tertiary alkyl halide. This nucleophile doesn't want to get in there. What would be the product? Don't form much of this, so it would do elimination. It could pull off hydrogens here. That eliminates, puts the double bond there. Alright, so yeah, the alcohol chapter, how to form alcohols, reduce carbonyl compounds, forms alcohols. We looked at Grignard's reacting with carbonyl compounds, forming alcohols. What might this product be? So on the quiz it said, write a balanced chemical reaction for sodium reacting with an alcohol. Here's an alcohol part. Now we got a primary alkyl halide, strong nucleophile. Let's imagine SN2, 4. My students like ring closers and ring openers. This would be a ring closer. Closes up into a ring. Also looks like a Williamson ether synthesis. Well, I have a couple more examples prepared. We'll do that on Wednesday. So onward to new and exciting things. So I told you when we went over the quiz, that one question, I mentioned it. The reason why you don't want to ingest much methanol at all is your body oxidizes it, probably with the same enzymes, forms some formaldehyde. You don't want that in your body, but that next enzyme, we have alcohol dehydrogenase and the acetaldehyde dehydrogenase. It probably doesn't differentiate between acetaldehyde and formaldehyde. And here is formic acid. Any entomologists in the room? Formic acid might have been first discovered by an entomologist by distilling some ants. So how many of you have ever been bitten by a red ant? Yeah, so they form formic acid in it, and the bite is really just a formic acid burn. And it's this formic acid which destroys your retina real fast. So that is how methanol, why it's more toxic than methanol. Ethanol gets turned into acetic acid, which is salad dressing, or normal body metabolite. This is not a normal body metabolite. Ethylene glycol oxidizes to, I had 2 L's in my spelling of oxalic acid. Horrible. Which is toxic because it forms a precipitate in your body, the calcium oxalate. Treatment for these poisoning is tie up the liver. So if you accidentally drink some ethylene glycol and you call poison control, they might say, do you have any whiskey? Start pounding that down. It ties up your those enzymes, so you can form these things at a slower rate, and hopefully your body never reaches a toxic level where it causes all the harm that it can cause. Alcohol as a nucleophile. And we saw this in the fall with most of our SN1 type reactions, either with water or an alcohol adding to a carbocation. Alcohols are weak nucleophiles. Alkoxides are strong nucleophiles. We can get new oxygen-carbon bonds to form and oxygen-hydrogen bonds break. So here is alcohol as an electrophile. Of course, we form it with sodium. So you have a quiz question on that. I should point out a reagent that works just as well is sodium hydride. Works like that. You get hydrogen gas out of it, you still get your alkoxide. And that alkoxide can react with a alkyl halide, and here we see an ether forming. So here's a benzene ring. When you have just a methyl group on a benzene ring, you have this stuff called toluene, which you can buy at the hardware store. And so you see toluene in there, so here's para, meaning over at this position, p-toluenosulfonic acid, that's a mouthful, so we like to say TSOH. And here is an alcohol, and notice this is the bond that gets cleaved, the hydrogen-oxygen bond, and you can see it's like a hydrolysis formed with water, and it's in equilibrium. So this thing here we call an alkyl tosylate. Kind of like if this whole thing was a halogen, we'd have an alkyl halide. But we don't have an alkyl halide, we have an alkyl tosylate. Why did I bring up the alkyl halide? Halides are good leaving groups because they are weak bases, or the conjugate base of the strong acid. So the whole point of this is to make a good leaving group here. And we can do a substitution reaction. Alcohols can be converted to tosylate esters through a condensation. Condensation is the opposite of hydrolysis, but that's pretty related. And the tosylate group is an excellent leaving group. Now, all the substitution reactions that we studied that we did with an alkyl halide, we can do the same thing with the corresponding alcohol by making a alkyl tosylate out. And just as substitution and elimination were tied together with the alkyl halides and like strong bases. So here is a tosylate forming reagent, be the corresponding acid chloride. Maybe we'll see that. It's really not important. You still get the tosylate. So here's an alcohol. Your reactant formed the tosylate, and then a nucleophile can come there, and this is now a good leaving group, and it leaves. And there is the substitution. And then, of course, the elimination, similar thing can occur. So in this portion of the chapter, we're going to look at seeing how we can form a bromide from an alcohol, or we can form the tosylate. And there's a stereochemical reason why we would do one or the other. So notice here, imagine I had S2-butyl alcohol. Imagine this was a hydrogen. So I'd have a 1 enantiomer. I got a stereocenter there, and I form the tosylate, and the tosylate hooks on, pulls off the hydrogen of the alcohol. So this still has the stereochemistry of S. Then here's my nucleophile. It hits SN2 inversion of the stereocenter, and now I have R, 2-butyl iodide. This reaction shows the SN2 displacement of the tosylate, and we still have an S tosylate, and then when the iodide hits, we get an inversion of the center. So this thing needs the tosylate ion. When there's a hydrogen there, you have the acid we just mentioned. So here is the acid's conjugate base. And you could draw those jumping down there, jumping up there, and you can delocalize the charge. So the tosylate ion is a particular stable anion, so it's a nice leaving group. So these are all alcohols that have been converted to the tosylate. This thing here seems a little, why would we do that? Well, instead of a hydroxide, we could use an alkoxide and get an ether and form an alkyl halide. So all these nucleophiles can be substituted on there. Or we could reduce this to the alkene. So from a tosylate, from an alcohol, a nitrile, an alkyl halide, an ether, ammonia can hit on here. So we get an amine salt, which we can probably add some acid and get the amine. We wanted to form just an amine. So different ways to reduce an alcohol. So it has to go to the alkene. So here we see acid catalyzed dehydration of an alcohol to an alkene, and then we can do catalytic reduction of the double bond, hydrogen, pressurized hydrogen gas, and platinum or palladium catalyst. We effectively move the OH. Or here we take the tosylate, and I said there's the acid chloride derivative. This H and chlorine make HCl, this hooks right up. There's the tosylate, and there it is being reduced with a lithium aluminum hydride. And I'm going to save a bunch of my good stuff for tomorrow.